welcome to the class today. Today, we're talking about matrices and determinants. When we talk about matrix is a word first used in 1843 by a man called James Silvestri. What was he talking about as far as metrics is concerned? Matrices is just all about complex or real numbers which can be placed inside, which can be arranged in rows and columns. But the question is this: what are the importance of the matrix itself? For example, you run a very big firm, probably like companies or even holdings. Several companies becoming holdings. Now, for example, you have such a thing and you want to pay salaries of workers running into thousands. You can arrange their salaries in tiers or arrange in matrices in sense that when you have, and these workers, for example, they are grouped. There are salaries that are paid. Maybe you are paying some group of people 120,000. Maybe those people, there are about 27 of them. Maybe there's others that are being paid 200,000. So from there you can arrange them in rows and in columns. These are some of the importance of matrices. So you can use them to determine arrangement of payments. You can use them to determine arrangement of duties and so on and so forth. But today we'll talk about matrix from talking about the rows and column arrangement of matrix. Let's start from here. Now, basically, if you have something of this nature, if for example, I have A, B, C, D, E, F, G, H, I, and I place it inside a coiled brace like this. This is matrix. But the thing is, these are rows, and these are columns. So you have the rows and you have the columns. So the ones that are laid like this are the rows, and the ones laid in this direction are the columns. But the question is this: these rows and columns we're talking about, how do you name them out in figuration? There are sometimes we have metrics that are, maybe you have A, B, C, D. If you have metrics of this nature, it has, how many rows is this? You have 1, 2. This matrix has 2 rows and 2 columns. So because it has 2 rows and 2 columns, what you call it, the name is now is a 2 by 2 matrix, or you can call it 2 times 2 matrix. So basically we have, you can call it 2 by 2 matrix, or you can call it 2 times 2 matrix. But what about a situation where you have another one that is maybe A, B, C, D, E, F? This time you have how many rows? 1, 2. And you have how many columns? 1, 2, 3. So that gives you 3 by 3 matrix. 3 by 3 matrix, or you call it 2 by 3 by 2 matrix, or you call it 2 by 3 matrix. It depends whether the row comes first or the column, or you can call it 3 times 2 matrix. Depends on you. The reason is because I can take that fact from De Morgan. How? Because 3 times 2 is equals to 6, and 2 times 3 is still equals to 6. That's De Morgan's rule. Now, from here, this is the definition of matrix. You can take it from here that rows, columns, rows, columns, rows, columns. So whenever you see something of this nature, you can call this 2 by 2 matrix, and you can call this 3 by 2 matrix, or 2 by 3 matrix. But what about if you have the one of this nature? You have in A, B, C, D, E, F, G, H, I. When you have this will be 3 times 3, or 3 by 3 matrix. So we now understand what matrix is all about. Good. Now let's see matrices in different direction as far as laws of algebra is concerned. So in continuation from where we stopped, you'll discover that we can talk about several things as far as metrics is concerned. Now, first of all, we'll talk about equality of matrix. Matrix can be equal. Now, let's take a look at this. If, for example, you have equality of matrix, so matrix can be equal in the sense that if I have A, B, C, D, if these two matrices is equal to 4, 6, minus 3, 8, then what it means is that the elements of this matrix is equal to the elements of this matrix. That is to say, A is equals to 4, meaning this. It also shows that C is equals to 6. It shows that B is equals to minus 3, and it shows that D is equal to 8. So these are elements of matrix. A is this and this is this. So now, for example, if I tell you that matrix A is 28, 6, 9, X, and I tell you that matrix B is 4 minus Y minus Y, okay, this is W, that's minus Y. I have this to be R, and I have this to be 16. If I have these matrices like this, it's easy for me to say that find the value of X, R, and Y. If you have to find these values when A is equals to B. So therefore, what it means is that if you have this 28, 6, 9X, it shows that it's equals to W, R, minus Y, and 16. Now, if you have this, that is, what does it mean? 28 is equals to W. So, probably plus, we also have W too. Now, W is equals to 28, corresponding. What again does it mean? 6 is equals to minus Y. So, therefore, Y is minus 6. If 6 is equals to minus Y, if you divide both sides with a minus, you have Y to be equals to minus 6. So, from there too, you can have R to be equals to 9, corresponding. And the last one is that X is equals to 16. So this is equality of matrix. Some of them can end up becoming equations, but this is equality of matrix. Now, from equality of matrix, it's easy for us to now talk about something else called square matrix and rectangular matrix or whatever, but square matrix better. Now, if you have matrix, you say it's a square. Say it's a square matrix. It's a matrix, it's a square matrix. If a matrix is a square matrix, what it means is that it always gives some, or maybe it's a rectangular matrix, it's a square matrix. It depends on the shape that the matrix gives. That is to say, the shape that the element of the matrix curve out. Now look at it, for example. If you have A, B, C, D as a matrix, this is a square matrix from the word square. And don't forget, a square, all the two sides of the square is equal. Here is equal to this and here is equal. So if you look at this can be traced out as a square. So that's a square matrix. But I can also say a rectangular matrix because I can have something of this nature. 9, 6, 2, 4, 3, 8. If I have something like this as a matrix, this one is no longer a square matrix, but it is a rectangular matrix, because when you trace it out, what it gives to you is something like this, where these two sides are equal and these two sides are equal. So this is matrix. Now from there, we'll move from that phase to something else that has to do with matrix. Let's talk about that thing called unit matrix, and then we'll move to addition and subtraction of matrices. Now let's talk about the unit matrix. From the unit matrix, it's easy. What's a unit matrix? It's easy to say that when you have a matrix, there is an axis of the matrix called the principal axis. Maybe you have 1, 1, and 1. So you have 0, 0, 0, 0, 0, 0. This is a 3 by 3 matrix. But being a 3 by 3 matrix, you observe that this particular diagonal of it is all unity. It's all total unity. That is why it is called unit matrix. So all this diagonal is all unity. Unity means 1. So this is a 3 by 3 unit matrix. So sometimes you can have matrix that is 1, 1, that's 0, 0. This is a 2 by 2 unit matrix. So sometimes for the 2 by 2 unit matrix, you can write it as 2. But for 1, 1, 1, 0, 0, 0, 0, 0, 0, you can have I3, which is a unit matrix for a 3 by 3 matrix. But one thing about unit matrix, it is only affected by a matrix that is a square matrix, which you already know what a square matrix is. It can only be affected, it's an attitude of a square matrix. Only a square matrix can be a unit matrix. If you look at this matrix, it's a square matrix. Both sides are equal. And this is also a square matrix. So it is only a character that can be, is only a square matrix that have the behavior of being a unit matrix. So always remember, sometimes this I square, I2, I3. I2 means for 2 by 2 unit matrix. I3 means for a 2 by, just like that. But we'll talk about that in about the calculations. Now from here, it's easy, but sometimes you can have just I, capital letter I. Sometimes you can have just capital letter I. But you will understand that it's either a 2 by 2, a 3 by 3 matrix, but it's always a square matrix. Now, that is there for unit matrix. Now, let's talk about adding matrix together. Addition and subtraction of matrices. Let's see. Addition and subtraction of matrices. So, 1 is a matrix. Several is matrices. So, you can relate that in English in singular and plural. Now, from here, if you want to add matrix, you add just the normal way you do your normal addition. Addition of matrix and subtraction of matrix. Deal with addition and subtraction of the elements of the matrix. Look at this, for example. If you are having A is 4, 2, 6, 1, and you have B to be 3, 9, 0, 4, if you have something like this. If you say A minus B, let's start with A plus B. If you say A plus B, what you get from A plus B is adding the elements together. A plus B will give me 4, 6, 2, 1 plus 3, 0, 9, 4. This is what it will give to me. So from here, what do I do? 4 plus 3, directly 4 plus 3 is 7. 2 plus 9, that will be 11. 6 plus 0, that will be 6. 1 plus 4, that will be 5. That's matrix. But what about a situation it is A minus B? A minus B becomes 4, 6, 2, 1 minus 3, 0, 9, 4. That gives me 4 minus 3 is 1. 2 minus 9 is minus 7. 6 minus 0 is 6. And 1 minus 4 is minus 3. So you can have this as addition and subtraction of matrix. So addition and subtraction of matrix is all about the elements. Just deal with the elements of the matrix. We are good. Whether it's 2 by 2, whether it's 3 by 3. But there's something you must note about matrix. Matrix that can be added or subtracted can only be matrix that have the same number of rows and number of columns. Number of rows and the same number of columns. The only way you can subtract or add matrix, one of the conditions is that that matrix must have the same number of rows and the same number of columns. You can see from your in calculations. So from here, we've talked about addition and subtraction of matrices. Let's talk about the multiplication of matrix. Now, from the multiplication of matrix, it's easy to talk about the fact that if I have something of this nature, I can have something called, before I start the multiplication, I'll talk about scalar multiplication. We'll talk about the scalar multiplication first. For scalar multiplication, what's a scalar? Mathematically, a scalar actually means that value that you can use to multiply other values. So, in sense, if I have something like this, I have A to be 4, 2, minus 1, 3. If I have this as a matrix, and I'm asked to find 3A, it means 3 times A. That's what it means. So if I'm asked to find 3A, what it means is equals to 3 into bar 4 minus 1 to 3. So let's open that brace now. If you open the brace, 3, 4, that will be 12. 3 this is minus 3. 3, 2 will be 6, and 3, 3 will be 9. So this is scalar multiplication. So automatically, you can have questions that are scalar multiplication that can be forward on both sides, depending on how the question comes. Simple enough. You can have, maybe you are giving Q to be equals to 6, 3, 4, 9, 2, 1. And you are giving R to be 8, 2, 0, 1 minus 1, 4. If you are given this and you are asked to find 3Q plus 2R. That's one. And probably figure 2, you are asked to find 4R plus minus Q. You have to find this scalar multiplication. Now from here it's easy. Let's just take solution for that. So the first one, if you have this, 3Q this, that will be 3. For Q will be 6, 3, 4, 9, 2, 1. Plus, what you have for arrow is 8, 2, 0, 1 minus 1, and 4. So automatically, this will give us 3 times this. Will give us 3. This will give us 18. That will be 9, and that will be 12. So automatically, if you multiply this again, that will give us 3, 9. So you have 3, 1. That will be 3. And that will be 6. And that will be 27. 27. So automatically you're having plus, what I have here is 2A to be 16. That will be 2. That will be 4. That will be minus 2. That will be 0. And that will be 8. Now you have this, you multiply them. Now just add them up. When you add them up, you have 18, 16. 1816 becomes, you have 8 plus 6, that will be 8 plus 6 will give us 14. So you have your 4. You have your 4 carrying 1, that will be 34. So you have 29. You have 29. You have 13. You have 6 plus minus 2, you have 4. You have 12 plus 0, that's 12. And you have 3 plus this, and that will be 11. So automatically you have that. So I've taken this already. So you will take this as your own practice question. So from there, we've come to the end of scalar multiplication. Now we're going to talk about matrix multiplication, which is the next stage of multiplication. Now for matrix multiplication that we want to talk about now. We've talked about scalar multiplication. Now we want to talk about matrix multiplication. Now for matrix multiplication, it's simple. All you just need to do is column or row times column of the other. Now in variance, if I have A to be equals to 4, 2, 3, 1, and I have B to be 6, 1, 4, 3. If I have this, and I ask you to find AB. If I'm to find AB, it's simple. All I need to do is take a value 4, 3, 2, 1. I take the brace 6, 4, 1, 3. I start with this. Now it's easy for me to multiply now. All I need to do is to use the first row to multiply the columns of the next one, then the second row to multiply the columns of the next. Now look at this. It goes like this. This is the first row. The first row times this times this. The first row times this times this. Now, let's start with that. So, that's 4 times 6. 4 times 6. The next thing is 2 times 2 plus 2. You see, I put the positive sign out. 2 times 4. So I take it 4 times 6, 2 times 4. So I've used the first row to multiply the column. So I will now take the same first row to multiply the next column. That will become 4 times 1. You see, I give space. Plus 2 times 3. 2 times 3. So I have this. So I'll come back again. I'm done with the first row. Let me now use the second column. The second row, will give me 3 times 6 plus 1 times 4. So I will now have, the next one is 3 times 1 plus 1 times 3. So finally that gives me 4 times 6 automatically will give me 24. 2 times 4 will give me, that will be 24 plus 8. And this will be 4 plus 6. And this will be 18 plus 4. This will be 3 plus 3. So finally will give me 24 plus 8. 24 plus 8 surely will give me a value which is 32. 32. 4 plus 6 will give me 10. 18 plus 4 will give me 22. And 3 plus 3 will give me 6. So automatically, you remember, row times column, column. That's for this. Row times column, column. That's this. So with that, you get your multiplication. So automatically, it's easy to, that's for a 2 by 2 matrix. What about if I have to take a 3 by 3 matrix? 3 by 3 matrix is still the same thing. Probably you have something of this nature. Maybe you have 4, 1, 3, 0, 2, 0, 2, 1, 3, 5, 7. And you are multiplying it with 1, 1, 0, 2, 4, 3, 5, 1, 2. You're multiplying with this. This is a 3 by 3 matrix. You're multiplying the two of them. Now, when you do that, what do? The first row times all the column. Let's go. The first row, let's stay with the first row times all the column. The first row will go. When the first row hits it, we'll have something like this. We'll be taking it directly now. We'll be taking it directly. So 4 times 1, that will be 4. 0 times 2. 0 times 2 will be 0. 3 times 5 will be 15. So those are the positive sign. So the same row again times the next column. 4 times 1, that's 4. 0 times 4, that's 0. 3 times 1, that will be plus 3. So the last one, 4 times 0, 0. 0 times 3, 0. 3 times 2, 6. So I'm done with the first row. Now we'll take the second row. The second row here will go like this. 1 times 1 is 1. 2 times 2. 1 times 1 is 1. 2 times 2, that's 4. 5 times 5, that's 25. So we are done with this. We'll go for the next one. 1 times 1 again, that's 1. 2 times 4, that's 8. That's 8. And we have 5 times 1, that is 5. So now you have 1 times 0, 0. 2 times 3. 2 times 3 for the next one will be 6. And the last, you have 5 plus, that's 10. So last but not the least is the last row. We're done with this now. So we'll take the next one. The next one will be 3, 1 is 3. So 1, 2 is 2. 7, 5 is 35. So we have 3 times 1, that's 3. 1 times 4, 4. And 7 times 1 is 7. So 3 times 0 is 0. 1 times 3 is 3. 7 times 2 is 14. So let's now add everything together. That will now give us 4 plus 0 plus 15, that's 19. 4 plus 0 plus 3, that's 7. That's 6. 1 plus, that's 30. That is 8 plus 5, that's 13. Plus 1, that's 14. 0 plus 6 plus 10, that will be 16. 3 plus 2 plus 35, so that will be 40. And 3 plus 4 plus 7, that will be 14. 0 plus 3 plus 14, that will be 17. So that is for the 3 by 3 matrix. So always remember, the first row times all the column, the second row times all the column, third row by all the column. So with that, you'll be able to get your direct value for matrix multiplication. Now we're done with that. It's easy for us to continue. We're going to talk about something we'll call transpose of a matrix. Transpose of a matrix. So we want to learn how to transpose a matrix. So when you want to transpose a matrix, it's easy for you to transpose a matrix. What is transposing a matrix? Transposing a matrix is all about making the row to become the column or the column to become the row. That's just what it means. So if I have A to be equals to 4, 2, 6, 3. So my A transpose, that is the symbolization of transpose. The T at the top is transpose. A transpose now becomes changing the row to become column. So all I need to do is, you have 4, 6, 2, 3. So it becomes 4, 6, 2, 3. What has happened? The row has now become the column. What you don't need to do, this is a stand, this is a stand. You take this, you stand it like that, you take this, you stand it like this. So the row is now the column. Now what about if the transpose is for 3 by 3? It's even simpler. All you need to do, remember, you are converting the row into the column. Now from here, if I have W as a matrix to be 4, 2, 9, minus 7, 3, 11, 13, 24, 10. If I have this, if I say that A transpose becomes, what do you get? 4, 2, 9. 4, 2, 9. What do you get? Minus 7, 3, 11. And this is the last one. I stand this, standing. I stand this, standing. And when I stand this, what happens to it? It becomes 13, 24, and the value 10. So ladies and gentlemen, that is that. So for transpose of a matrix, you convert the row into a column. That is transpose. Now we'll move from there to the next stage. And that will be talking about something we call the determinant of a matrix. Now for the determinant of matrix, let's consider the determinant of a 2 by 2 matrix first of all. Now, determinant of a matrix. Now for determinant of a matrix, you observe that it can be represented. If I say the determinant of A, I'll represent it as this, or it can be represented as det A. So it depends on whether it's this or det A. But what's the determinant? If I have a matrix A to be equals to 4, 6, 3, 2. Maybe I have this as 5. If I have a matrix like this, then the determinant of the matrix is this, which now becomes 4, 3, 6, 5. Now you see that the enclave of the det sign shows up. Now what does that mean? It shows that this matrix now become the principal axis times in it off. That becomes 4 into bracket 5, or 4 times 5, whatever you call it, is 4 times 5 minus 6 times 3. Depends on you. So if you look at this, you can say 5 times 4, this, 3 times. But always remember, it is this minus this minus. So from there you have 4 times 5 should be 20. 6 times 3 should be 18. So 20 minus that becomes 2. So that is determinant of a 2 by 2 matrix. But basically, it's easy for you to understand that if, for example, I have something like this, x, y, z, w. So my determinant become wx minus yz. Always remember that. Now from here too, I can say that sometimes can have equations where I have something like this. Maybe I have x. I have something like 3. I have 3. I have another x. So if I have something like this, my determinant will be x. That will be x squared. 3, that will be probably my determinant is equals to 0. For example, this is an equation. My determinant is 0. So if I solve my determinant here to be x, that will be x squared minus 3 times 3, that will be 9, equals to 0. If I take this across the equality sign, I will have x squared is equals to 9. I will have x to be plus or minus root 9, which is basic. So from mathematical computations, it gives me the fact that because when the square crosses the equality sign, the mathematical computation for that becomes plus or minus root of 9. So x now, within the limits of mathematical errors, this becomes plus or minus 3, which you people call minus 3 or plus 3. So it depends on you. Now from there, it's also possible to have statements like you having, maybe you are giving something like, probably you are giving values like root 2, you have this to be 4x, and you have 4x, you have minus 1, and you have 4. all equal to 0. If you have this, if you multiply, you have 4 root 2 minus 4x is equals to 0. If you move this, you have 4 root 2 is equals to 4x. If you divide here by 4, you divide here by 4. So x now become root 2. So you can have this. These are examples that can come out from what we call determinant of a 2 by 2 matrix. But let's go for the big boy. Is determinant of a 3 by 3 matrix. Go for the 3 by 3 debt matrix. So for the 3 by 3 debt matrix, it's simple. But all you need to understand is, since you already know how to analyze the 2 by 2 debt matrix, it becomes easy for you to analyze the 3 by 3 debt matrix. Now look at it. For example, if I have a problem of this nature, that I'm giving a matrix of a debt of 4, 2, 3, 1, 0, 9, 5, 7, 1. I have this. What I need to do is to apply Sylvester's theorem, or you can call it the debug rule. The debug rule or the Keybags rule. Depends on the debug or the Keybag. We can call it the Keybags rule. Now, if you have to apply the Keybags rule, the Keybags rule says all analyze on basics of human existence and human analysis and what they call it, psychological tinties. Maybe, probably you can call it a bazaar. Probably. Now, from here, if it's a bazaar, we will understand that sometimes, probably a bazaar, sometimes you say that in life that positive things can happen to you. It's also possible negative things can happen. It's also possible positive things not happen again. It's also possible negative things happen. This is the Keybags rule. It's the Keybags rule. It's the bazaar. Let me use that word. It's a bazaar. It's a bazaar. Positive can, negative can. Negative and positive. That is why they say that there is nothing after worst. So, good. Now from here, I can analyze this from this perspective to say that this statement here, 4, 2, 3, 1, 0, 9, 5, 7, 1, it's a bazaar. I can say this guy is positive. I say this guy is negative, and I can say this guy is positive. Depending, except when it enters 4 by 4, you can decide to apply the Saros rule. Probably not the Keybags notation. Good, from here, it's simple. I can tell you that I'll pick this first guy out. What's that guy? If I pick him out, that's 4. I take a smaller line. But now, after this 4, which row is this 4 covering? The whole of the row and its column is going to disappear. The row of that 4 and the column of the 4 disappears. Where's the row of the 4? This is his column and this is the row. This is his column and this is his row. So this is row and this is column automatically cease to exist. So what do we have now? We'll have 0, 7, 9, 1. Beautiful. That's it. So the next one is minus 2. A bazaar. A bazaar. For minus 2, where is his column? This is his column. It ceases to exist. And his row ceases to exist. So when his column ceases to exist, his row ceases to exist, what is left? It is 1, 5, 1, 5, what again? 9, 1. And the last, which is not the least, is 3. Is a bazaar. Is a bazaar. So plus 3. So what do you have here? This ceases to exist, and this also ceases to exist. So if this ceases to exist, this ceases to exist. So we have 1, 0, 1, 0. We have 5, 1, and we have 5, 1. So from here, you can take your normal analysis. 4 times 1 is 0. So you have 4 into bracket. 4 times 1 is 0. That becomes 0 minus, you have 7 and 9 as values. So automatically, if you have 21, if you have 21 in 3 places, what will it give to you? 21 in 3 places will surely give us 63. Good. So that's computation. So that will be 63. That will be 63, and that will be 1, 2 into bracket 1, and surely if you have 5 in 9 places, surely will give us 35, and that will be plus 3. And I believe if you're having something of this nature, 1, that will be minus 0. The reason is because 5 times 0 is 0. So we'll take it up now. So from here you are having 4, you are having minus 63. Oh, sorry, you have minus 63, you have minus 2, and that will be minus 44, and that will be plus 31. So finally, let's take this out. 4 times 3 surely will give me 12. I will have 2 carrying 1. 4, 6 will be 24, plus that other one will be 25. So that's 25, but it will be minus 25. Minus will give me plus. So 2 times 44, that surely will be 88. And that guy there, what's that guy? That's 3. So I have minus 252. If you add this together, that should be 1. Good. No, that will be 91. So if I decide to subtract my values, I will say 2 minus 1, that will be 2 minus 1 will be 1. And what do I have next? I will have 15 minus 9. If you have 15 minus 9, that will be 6. That will be 6, and that will be 1. So automatically, I have minus 161 as the determinant of the matrix. So, sorry, you can always take your computations the way you want it, depending on your analysis of what you call computable values. So, we've come to the end of determinant of matrix, multiplication, determinant of matrix. But now, let's not state something. Any matrix that the determinant is equals to 0 has a name. It's called a singular matrix. A singular matrix. So when your matrix is equal, when the determinant of a matrix, for example, is equals to 0, then the matrix is said to be a singular matrix. So when you are asked, prove that the matrix is a singular matrix, always remember that when you solve that matrix, the depth of the matrix is equals to 0. Then it shows that it is a singular matrix. Now for inverse of a matrix, we'll be summarizing it with the inverse of a matrix. It's easy. The inverse of a matrix is simply defined as if you have matrix A, for example, maybe you have matrix A, then its inverse is A inverse. So whenever you see that sign at the top, A raised to power minus 1, it's called inverse of a matrix. So basically, that minus 1 at the top is inverse. But don't forget, mathematically, A minus 1 also means 1 over A. That's inverse of a matrix. But sometimes you're asked to find 1 over A, which is A inverse. It's still the same thing. So, but the inverse of a matrix, the A inverse itself, is defined as 1 over A depth adjoint of A. So with this formula, you can find the inverse of the matrix. And where A can be any value, it can be B inverse, but remember it is 1 over determinant. We've already talked about determinant, so you know how to take determinant of a 2 by 2 or a 3 by 3 matrix. So, and the adjoint. For example, let's see determinant or inverse for this 2 by 2 matrix. For example, you are given A to be equals to A, B, C, D. Maybe I'll give you something like this. You'll discover that if I have something of this nature, the A det of this, the determinant of this will be AD minus BC. You already know that. Minus that. Okay. The adjoint of this will give me something of this nature. All I need to do when I want to take the adjoint of this is to interchange the principal diagonal. If I interchange the principal diagonal, what I have there will become DA. So I've exchanged them to DA. I've interchanged them. So after interchanging, what about the non-principal diagonal? What do? I will apply negative sign in the sense that become minus B minus C. But if you understand this, so from here, A inverse now, which is the inverse of A, becomes 1 over A det adjoint of A. So this is adjoint of A. So from here, A inverse now becomes 1 over, that is AD minus BC. The adjoint itself is D minus C minus B and A. So finally, I can just say that A inverse is D minus C minus B A divided by AD minus BC. So it depends on you. So that's inverse of a 2 by 2 matrix. But it's also possible for us to consider a question in that area. For example, you are told that probably I'm giving S to be equal to 4 minus 3. Maybe I'm giving 2, 5, or something like this. So I'm giving something like this, and I'm asked to find S inverse. The first thing I'll do is to find the determinant of S. The determinant of S is simple. That will give me 4 minus 3, 2, 5, which we all know to be 5 times this, that's 20, minus 3 times 2, that will be minus 6, so it's called minus 6, which we all know that 20 plus 6, 20 plus 6 will give us 26. So the determinant of S is 26 already. So if that is 26, then the next thing we are going to find is to find the adjoint. And how do we do that? Now finding the adjoint is very simple. The adjoint of this, the adjoint of S is simple. What you just need to do is, you bring the value, it's 4 minus 3, 2, 5. You reverse this. When you reverse the principal axis, reversing the principal axis will give us 5, 4. So what happens to this? You apply the sign. If you apply minus sign to minus 3, you apply minus sign to minus 2. So the adjoint becomes 5, 3, minus 2, 4. So therefore, S inverse becomes, what is S inverse? It becomes 1 over determinant of S, adjoint of S. And that automatically becomes 1 over 26. Then what's the adjoint of X? That becomes 5 minus 2, 3, 4. So that is the inverse of the matrix. So it depends on you. Sometimes you leave the answer like this, Or you can decide to open the bracket by making it 526 minus 226, 326, and 426, depending on you, any one of them you feel like. So, but always remember, the general formula for calculating the inverse of a matrix is 1 over determinant times adjoint of the matrix in question. So, now, that is inverse of a matrix. And always remember that simple formula for inverse of a matrix.